Hey everybody, make sure you all can see my screen. All right, welcome to topic number 9 called functions. Okay, so before we talk about what a function is, let's take a look at this thing called the set notation and interval notation. If you took Math 108, we talked about something called the interval notation before. Interval notation is designed to express answers using involving with inequality. We also use interval notation for domain and range. So I will explain that just in a little bit. All right. So what is a set notation? Well, a solution set. Okay, this word first. A solution set is referring to a set of all solutions. It's like a basket. Okay, it's a basket that can actually that contains all your answers. Now we're going to use brace. Okay, we're using brace as for our set notation. So for example, x greater than 8. Okay, there are a lot of numbers greater than 8. So x greater than 8 means we are looking for all the numbers that are bigger than 8. And you can imagine there's tons of numbers bigger than 8. So how do you actually include all those answers? How do you include all those numbers that are bigger than 8? So the solution set, or it's something called the set builder notation. Okay, we will use set builder notation to include all the answers. So this notation, okay, with the brace means we will read them as is the set of all x's. The slash here means such that. It's a set of all x's such that x are greater than 8. All right. So using this basket, okay, it allows me to include all the answers. Now, if I only have one answer, like x equal to 8, x greater than 8, there's a lot of numbers bigger than 8. But if it says x is equal to 8, that means my answer is 8. So in my set notation, I will simply just write a brace with the 8 in there. It's basically a basket that contains my solutions. Okay. So this is just a very fancy way of writing your your set builder notation. So rather than using set notation for inequality, we can use something called the interval notation. So here I'm trying to establish that using set notations, okay, when your answer is finite, one answer, two answer, three answer, okay, or it contains an equal sign. Your solution contains an equal sign, we can use a set notation to express our answer. For anything more than that, if we have infinite number of solutions, we need to express our answer using interval notation. So interval notations is used to describe solutions within certain intervals using inequalities, or we can use interval notation to describe something called the domain and range. All right, so let me show you how to use the interval notation real quick, or refresh your memory on this. So if it's involving with the inequality, you always want to make sure you read the inequality from the variable. We always gonna write the interval notation from left to the right of the number line that we graph. Okay, either we graph it by hand or we graph it from the calculator. We always read our graph from left to right. Always use bracket when the inequality involved with equal to. Always use parentheses when it's involving with infinity, negative infinity, or simply just greater than and less than. But if there's an equal to, you gotta use bracket because bracket indicates that that value is actually one of the answers. Okay, so here I got two examples. X greater than 8. Think about numbers bigger than 8. That means 8 is not one of the answers. 8 is not bigger than 8. But I'm still using the number 8 as a reference while I'm writing my interval notation. So if I will kind of draw this by hand on the number line to express my answers, let's say 0 is here, 8 is right here on the number line. X greater than 8, if you read from the variable, numbers bigger than 8 got to be to the right hand side of 8. Okay, how right does your answer go? Well, it got to keep on going to infinity, right? There are infinite numbers bigger than 8. Since there is no equal to on the inequality, I will use parentheses. So I will say parentheses, all the answer to the right are my solutions. So in terms of writing it as an interval notation, we would just look at this, what we draw from left to the right. Left to right simply means you write your answer from small to large. So my solutions are from 8, but I'm using a parenthesis to tell the reader that 8 is not included, but 8 is like a reference, is where I can start. So my answer is starting from 8, keep on going. The comma means to infinity. My answer is from 8 to infinity, but 8 is not included. That's why I use a parenthesis. And that's how we actually write interval notation. All right, so let me draw this one. Express x is less than or equal to 8. That means I'm looking for numbers that are smaller than 8. So again, if 0 is here, 8 is here. Number smaller than 8 is to the left of 8. So how many numbers are less than 8? Well, infinite number. But on the number line, if you keep on going to the left, you are going to negative infinity. Since there is an equal to here, I will use a bracket. The bracket indicates 8 is actually part of my answer. Okay, 8 is less than or equal to 8. So when I write the interval notation, I simply write the interval notation from small to large, or left to the right of what we draw. So my answers are from negative infinity, using parentheses, always use parentheses on infinity, comma means 2. My answers are from negative infinity all the way to 8, using a bracket. Okay. So if we look at the answer horizontally, we always express your answer from small to large or from left to the right of what we draw. All right, we'll talk more about this. Okay. Identify whether relation is a function. Okay, so what is a relation? A relation, we're defining a relation is simply a set of ordered pairs. Okay, just like right here, what I typed out. 1, 2, 3, 4, 5. There are 5 points together with the brace. That means here I have a set of 5 points. Together we call them a relation. It is a set of bunch points. Okay, we're not connecting them. We just plot. If I plot them, I'm basically just plotting 5 random points. But together they are considered as a relation. The set consists of the first component of each ordered pair is called a domain. The first component of each ordered pair is the x. Okay, it's the x value. So here we are saying the first component, all the first component here, this is a comma, sorry. All the first component here is called domain. The set consists in the second component, or your second component, or the y is called a range. Okay, so I will define both of those words. So right now, this is just simply a relation. A function. This wording is a very, very strange, very vague word. A function is simply a correspondence between the domain and the range, such that every element in the domain correspond to exactly one element in the range. So the definition is not really saying a whole lot, because what is a domain and range? Domain normally is labeled as the x value or the input value or the independent variable. Okay, those are considered domain. In terms of a graph, is referring to how wide the graph is. Left to the right, domain is x value or how wide the graph are, or how wide the graph is. Okay, so y equal to x. If I want to graph simply y equal to x in a graphing calculator, to graph any equation or graph anything called a function, you simply go to y equal. And that's one of the reasons why in the previous topic we learned, we see that when you have linear equation in two variables, we always solve for y equal. We put them in y equal because we're trying to view them as y equal to mx plus b. But other reason solving for y is because that's the way how we actually key in the calculator. Okay, there's a reason for it, and the big part of that reason solving for y to matching the form y equal to mx plus b because the word function. So here on the graphing calculator, I simply just have to type in the letter x. Okay, y equal to x. I just type in x. X is right here, right next to the word alpha. Okay, so so if this is the first time you're dealing with a graphing calculator, so let's make sure everything is set up correctly. Right above the word window, there is something called a table set. So we press second and table set. Make sure your tablet starts at 1. Okay, and it's actually the numbers are 1 at a time. Your independent and dependent variable, make sure it's set on auto. So it will display all the numbers that you need. All right, we do one value at a time. The way how we set up, basically we started with 1, okay? And then the next number will be 2. The number before 1 will be 0. The one before that will be negative 1. So the way how we set up the table, we're not dealing with decimals or fractions. All right, press the word zoom next and choose number 6, zoom standard. That means it will display the standard window. The standard window is from -10 to 10 on the x-axis and the y-axis. So this is what y equal to x looks like. It's a straight line, simply a linear equation. Let me paste it right here. So domain is about how wide the graph is. So remember, straight line never ends. This side keep on going, and this side keep on going. Okay. So if you will look on the top right, this is going which direction? This line on the right side is going at which direction? So if I draw this from left to right, this arrow is pointing to the right and is also going upward at the same time. The other side is going to the left, but it's also keep on going down at the same time. So left to the right, how wide this line is, how wide is this graph? And that's called a domain. Okay, domain is referring to all the x values on the graph. It's also, but if you actually look at the graph itself, it's about how wide the graph is. So for a straight line, your domain, how wide it is, it got to be from negative infinity, go from small to large, okay, left to right, from negative infinity all the way to positive infinity using interval notation. Down and up, okay, when we talk about range, range is labeled as a y value or the output value, or sometimes we call them dependent variables, okay? Or when we're actually looking at the graph, we can say how tall the graph is, how tall it is. Well, this size keep on going down, the other sides keep on going up. So small to large, down to up. Your range is actually also keep on going down, 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 keep on going up, up, up. It's actually from negative infinity to positive infinity. So the domain and range for this equation, for this linear equation, is the same, negative infinity to positive infinity. Okay, we are looking at this graph. It's not just a straight line. We are actually looking at them as in terms of, okay, left to right, down and up. What you do not see is the points. There are infinite number of points on here. Okay, there are infinite number of points. So we need interval notation to include all those coordinates, okay? So domain and range is simply a way to include all the x values, all the y values on that graph. So let's reread our definition of a function. A function is really a correspondence between x and the y, x value and the y value, such that every element in the domain in x value or in x correspond to exactly one element in y. Every x corresponds exactly one y. A function is a correspondence between x and the y such that every x value corresponds to exactly one y value. If that exists, that's considered as a function. All right. So let me give you an example. Boys and girls. Boys are x, girls are y. All right. For every x, it can only correspond to exactly one y. So this is okay, right? This is actually okay. Every x corresponds to exactly one y. Now, same thing, boys and girls. Every x, so if the x are the same, but different girls, same boy, different girls, not cool. So that is not a function. All right. But if you have the same x, excuse me, different x, but correspond to the same y, then that's okay. Because by the definition, it says every x can only correspond to one y. You never say the same x. Okay, see, this part is a backwards what the definition is saying. All right. This is actually not every x. This is the same x correspond to exactly the same y. That's not what the definition is actually trying to say. Definition is trying to say every different x only correspond to exactly one y value. All right. So to consider a relation to be a function, to consider a relation to be a function for any, if you got a set of points, for those points together to become a function, you just got to make sure the relation does not have the same x value. And as you can recall, what kind of line has all the x value that are the same? What kind of line that we drew from the previous topic, all the x values are the same? Vertical line. Okay, vertical line. The key characteristic for vertical line is all the x values are the same. Okay, so because of that, we're actually going to use something called, we're actually going to use vertical line to testing some of these graphs, whether those graphs are a function or not a function. So to be a function, you cannot have the same x value so that every x value corresponds to exactly one y value. All right, so consider the relation below. So here is again the same 5 points. What find the domain? Domain are the x value. All right, so all we had to do is write our answer in set notation. So the domain, the reason why I'm writing as a set notation because my domain here are finite number of x value. It's not infinite. So my domain put in the set notation is simply 2, 4, -3, -2, and 4. So I'm just gonna write from smaller to the largest, okay? My domains is -3, -2, right? 2 and 4. Domain is x values. Range is referring to as the y values. So my range put in the set notation. All right, all my y values. So what do I have here? -3, excuse me, -4, -3, -4, -3, -1, and +2. So here are my range for the entire relation. I'm gonna ask you, I'm gonna plot these points real quick. 2, -3, to the right 2, and down 3. One, two, three. Okay, that's the first point. 4, 2. -3, -3, -3, 1, 2, 3, -3, 1, 2, 3. It'll be right here. -2, -1, -2, -1, just right here. All right, so these points, I'm not connecting them, okay? I'm just plotting them. These 5 points together is called a relation. 4, -4, to the right 4, down 4. All right. So, what do you think? Is these 5 points together a function or not a function?
It's not.
Very good. Why?
It doesn't
Because,
pass the vertical line test.
well, vertical line test is used for an actual graph. This is 5 points, but that's the right idea because I have what? I have the same what? X value, right? See these 2 points right here on top of one another? Look like a vertical line, right? If you connect them. So it's not a function because the x values are 2 x values are the same. All right. So remember, if you're just looking at bunch of coordinates for that for all those coordinates together for that relation to be a function, you cannot have the same x value. All right. So again, the word function is very, very vague. Okay. To be honest, it's basically a word all of a sudden thrown to you, but nobody can really explain it what that is because function is a lot of different things. All right. So when I use the word function, I'm referring to as 2 different things. It's almost like what I was trying to explain about equation of the line. The equation is the line is the equation. The word function is referring to the equation. The word function is also referring to as the graph of that equation. There are 2 different aspects we are looking at. Okay, equation aspect, but we don't use the word equation anymore. We're just basically using, we used to have equation on the line. We basically put 2 words together as one, call them a function. So the function notation, y equal to f of x. If you ever seen this notation, y equal to f of x, it defines a function named f. That is y. This is literally saying y is a function of x. Okay, y is a function of x. So we are changing the name. We don't call them equation. We don't call them a graph or straight line. We just simply using one big word called a function. Okay. So what this is explained is to be a function. Okay. To be a function, you cannot have the same value. So if a graph is not a function, we can actually use the word called relation. That relation is not a function. I will show you some pictures that is not a function. Okay. So think of your body system, okay, like a function. You input X value. This morning, you input something in your mouth, right? Later on, we're gonna go to the bathroom and we're gonna output, right? You input X and what you output is always the y value. So every time when you substitute a number for an x into the equation before, the answer you always come up with at the end is the output. Okay, so function, just like, basically you eat something in your mouth, your digestive system is basically your entire function. Your food work its way out at the end. That's your output. Okay, so you can think of a function is working like that. It's a functioning things. Okay, things are happening throughout the entire process. So later on, I will give you a little bit more complicated function so you can see how we can input an x value and and work it out and where we end up with an output. All right, linear function. So every equation we saw before is actually a function. There's a graph associated with it. Linear function. The standard form for a linear function is your y equal to mx plus b. But now we're replacing y with f of x because y is a function of x. Okay, so if I simply graph, earlier I just showed you, I graphed something called y equal to x in the graphing calculator. Technically, I was trying to graph what f of x is equal to x. So when we graph f of x equal to x, you simply get a linear function. And the standard linear function looks like these. Okay, just a straight line. Let me make it a little bit smaller. It's all right. All right, x squared, quadratic equation. Now we call them quadratic function. All right, quadratic function, the most basic one is called x squared, or we call them a parabola. So I go back to my y equal, I press x, caret key for exponent to the second power. Now, if your graphing calculator display doesn't quite look like mine, that's okay. That just means you have a different type of display. Just watch out where the cursor is. Sometimes the display, sometimes your calculator might have like an X, right, with a little box. So when you put a 2 in there, the cursor is actually sitting on the exponents. Okay, so to come down from the exponent, you simply press the right arrow key. All right, so I'm gonna graph it. I already set up my table earlier, so everything is standard. So this is what my quadratic function looks like. It's a parabola. Okay, this U looking thing is called a parabola. We'll talk more about it. All right, the parabola can open up or it can open down. As a matter of fact, a parabola can open to the right and open to the left. Okay, but open left, open right is actually not a function. Those relations are not a function. So to be so for parabola to be a function, it normally opens up or open down. All right, we review a little bit about rational expression. Rational expression are called the rational function here. There are two versions of it. Okay. I'm not too. I don't want you to look at the picture so you know. I wrote two different rational functions here. What the difference is the exponent on the variable. Okay. If it is 1 over x to the first power versus 1 over x squared. Okay. Odd exponent versus even exponent. The graph looks slightly different between the two. So I'm going to do a basic 1 over x. Now my syntax here is a little bit, my syntax, what I key in the calculator might be a little bit different than yours. So I got to be very careful how I type it in. 1 over x is actually better for me to type in 1 divided by parentheses with the x. Because when I have a variable in my denominator, it's safer for me to put an x in there, x inside the parenthesis. Okay. Otherwise, it might not draw what I want to see. Now, if your syntax look like the way how I type here, just make, you don't need a parenthesis for it. Only if your text look like mine. All right, once I graph it, this is what 1 over x looks like. It's a rational function with an odd exponent. Okay, this graph is not very clear. So what we're gonna do here is we're gonna change its window a little bit. Okay, for this thing to pop out a little bit better, what I'm gonna do is I'm gonna squeeze my windows. I'm gonna squeeze, I'm gonna squeeze them in from left to right, and I'm gonna squeezing up and down. I'm gonna squeeze them. So the way I squeeze them is simply go to my window. Remember, my window is from -10 to 10, right? If I want to squeeze it inward, that means I need to have my minimum for x set at -5, my x maximum sets at +5. That's how I'm squeeze it from left to right. All right, squeeze it up and down is y minimum. I can put it down to -5. Y max, I can actually decrease it down to +5. So I'm squeezing in along the x-axis and the y-axis. So now my graph will pop out a little bit better. There you go. That's a little bit better picture. This is what a rational function looks like. Now we did talk a little bit about finding a little restriction. Okay, finding the restriction on the variable. What x cannot be. So by simply looking at this, the way how we did to find the restriction on the variable is simply set the denominator not equal to 0 and solve for x. But here you got nothing to solve. So the restriction here is this variable x cannot equal to 0. And it tells it actually shows me that on the table. All right, right above the word graph, there's a word table. So if I press second and graph, it displayed my table. Remember my table started with 1. All right, if I go back up a couple of places, okay, see all I have here is integers. So when x equal to 0, the y value display as an error. Okay, because ahead of time I already know x cannot equal to 0. That's why the error message shows up right here. All right, I'm gonna go back to y equal and grab this function 1 over x squared. So now I'm adding the exponent onto my variable. So it definitely makes sense that this x squared got to be in the parenthesis. So I'm gonna say x raised to the second power and close the parenthesis. If not, I'm afraid, if not, I would not even know what that square is gonna do. But in this case, I know the square is on top of the x just by simply put them in the parenthesis. All right, so remember my window it was still squeezing, right? Remember my window earlier was still squeezing. So if I press zoom and number 6, it will take me back to standard window. It will make it look like that. So let me go squeeze them again. I want the graph to pop out. All right, y minimum, y maximum. Make sure you understand the minimum got to be smaller value than the maximum. Otherwise, it will not graph for you. All right, so this is what 1 over x squared looks like. Okay, it's a rational function. And if you set the denominator, not equal to 0 and solve for x, you will notice that x is still cannot equal to 0. All right, my restriction on the variable. Okay, if I set my denominator not equal to 0, so now I'm solving a quadratic equation with only 2 terms. So all I need to do is take a square root on both sides, and square root of 0 will still be 0. So that's how we get x is still not equal to 0. All right, if I go to my table, you will see when x equal to 0, it's the same error message. All right. Just want you to see the difference between the two rational functions. So far we got linear function, what they look like, straight line. Quadratic function is a U. Rational function, we got two different versions. R power, the exponent here are odd. Even power looks something like this. So if I will go back to y equal and changing the x squared to x to the fourth power, which is another even power, you're gonna notice that the graph will look very similar, okay, as a square one. All right, absolute value function. If I did not show you how to solve absolute value equation before, I will make sure I do that when we run into it. But for your absolute value, I'm trying to move this. Let me go to a graphing calculator. I'm going to show you what this picture look like. All right, I'm going to go back to the standard window because I'm about to graph a new graph. All right, go back to y equal absolute value of x. So I'm going to clear that. Go to math. Go to the right one to numbers. Number one, ABS, absolute value. Choose number one. And inside the parentheses, simply type in the x. And that will actually graph your absolute value function. It's a V. The V open up is my absolute value function. All right, x to the third is called cubic function. X to the third. So I'm going back to y equal, just clear that out. And say x raised into the third. This is what a cubic function looks like. Cubic function is also considered as what we call the polynomial functions. All right, square roots. We learned how to solve square root equation before. Square root equation, square roots, radicals are considered as a radical function. So I'm just give you two different example here. I'm gonna do a square root and a cube root. So square root function. So I'm go back to y equal, clear that. Second square root, put an x in the side of the parenthesis. Or if you put x underneath the square root, if your syntax is a little bit different than mine. All right, and graph it. This is all square root function looks like. So if you don't have a graphing calculator, that's okay. You can just kind of hand draw this for right now. Okay, so you have an idea of what they kind of look like. All right, cube root function. So for cube root, we got to go back to math, or yeah, we got to go back to math. All right, under math, go choose number 4. Number 5 is for anything higher than a cube root. Okay, so for cube root, I can choose number 4. I'm gonna put my x inside that parenthesis again. So cube root of x is the graph look like this. So remember we mentioned that square root or even roots a negative cannot be inside. A negative number cannot be inside of an even roots, right? Like square root of -1 is an I. So that's the reason why when x is negative here for the square root, there's no graph here because none of that exists because it's all imaginary numbers. All right. But a negative number can exist inside an odd roots. That's the reason why when x are negative, there are y value, there are outputs right here. Okay. So that's why, don't be surprised why there are negative numbers inside the odd roots because they do exist. Negative number can be inside an odd roots. So make sure you know what these basic graph looks like. Okay. And there are more. I'm not gonna do it right now. There are more basic functions like x to the fourth power, but I'm not gonna graph that right now. I'm gonna do it later on the semester. I will show you the x to the fourth power. Okay. But I want to draw out the graphic. I want to show you these basic functions so we can talk about its domain or the range. So earlier I already showed you that linear function, the domain, right? This side and this side, right? Keep going right and up versus keep on going left and down. So the domain from left to right or small to large got to be from -infinity to infinity. The range here is set. The range is set for linear function. So the range here down and up got to be from -infinity to +infinity. All right. Parabola, the U. Okay. The U, if you look up here, this arrow, where is that arrow pointing? This part is keep on going left and up. This side is keep on going right and up. So in terms of the domain, keep on going left, keep on going right. So from small to large, if I were actually draw it the way it's supposed to draw from left to the right, my domain, my U got to be from -infinity. Keep on coming from the left and keep on going to the right. The range will vary. Okay, the range will vary for for your quadratic function, but for this particular example, this point got to be the very bottom of that U, and most of y'all can guess that very bottom is got to be 0 at the origin. So remember, the range is referring to as the y value. So when we talk about range, you got to look at the y value of the coordinates. Okay, down and up, down and up. So if this point is the very bottom, then your range must be starting at 0, the y value here. And this point is on the line, on the graph. So we have to include that y value. So that's why I use a bracket from 0, keep on going up to infinity. All right. Now, this rational function, we already determined x cannot equal to 0. So the graph from left to the right, okay, is coming. I know it's keep on going left on this direction, keep on going right here. Okay, coming from the left, okay, coming from the left. As I am approaching x equal to 0, my y value all of a sudden start dropping, okay, dropping a lot. Okay, but if you just think about in terms of left to right, the graph is coming from the left, right? Cannot be 0. So this graph also exists on the other side of the x equal to 0. Remember, x equal to 0 is actually what? The y-axis, right? Am I right? When x equal to 0 is at the y-axis, because we mentioned it before, on the y-axis all the x values are 0. So that's the reason why on the other side of the y-axis, the graph picked up again. So the domain got to be from -infinity all the way to 0. I'm using 0 as a reference, but I cannot include that 0 because I already know it cannot be 0. So that's why I use parentheses. Or my union sign means or my domain or my function exists on the other side of 0 and keep on going to the right to positive infinity. Okay. Now the range here varies, so I'm not gonna even attempt to write the range here. The range for rational function varies quite a bit. All right, same thing here for this even one coming from -infinity. All right, approaching 0, but it can never be 0. X can never be 0. And then I'm also, my function will also restart again, okay, from the right side of the y-axis or the right side of 0 and keep on going to the right. So the domain for both of these are the same at the moment. Union, that's a U from 0 to infinity. All right, parabola is just like absolute value function, okay? Their behavior is very, very similar. So the domain from this side keep on going left, that side keep on going right. So my domain is -infinity to positive infinity. And for right now, the range right here, the very bottom, that V is the same, it's in that same position as that U. So I can say my range is starting at 0 and keep on going upward to positive infinity. Cubic function. Okay, let's look up here. That part, I know it's going up, but at the same time, as I'm going up, I'm also going what? To the right. It's actually going right and up. This bottom part, I know I'm going down, but at the same time, I'm also going left at the same time. Down and left. Because your x value can, can keep on going to more negative. And the y value is also what? Getting more and more negative. That's what I mean by keep on going left and keep on going down. So domain and range for cubic function is already set. It's always going to be from -infinity to positive infinity for both. Okay, all cubic function has a domain and range are the same. All right, square root function, a little bit tricky. I'm not gonna do the range, okay? But for this example, I'm gonna do the domain at least. All right, right now I'm actually starting right here and going to the right. Okay, that's all I'm doing. So my domain, I can say, is from 0, right? And that point is part of the line. So I'm gonna include that 0, keep on going to the right. Okay. Square root is a little bit tricky. Cube root is actually already set. This side is keep on going left and downward. This side is keep on going to the right and upward. So the domain will be from -infinity to infinity. And the range is from -infinity to infinity. So just real quick, showing you all these pictures so we can actually begin to talk about how wide the graph is, or all the x value and the y value. So when we look at the graph, we talk about the wording we're using is left to right, how wide it is, how tall it is. But at the same time, we're also referring to all the x values, all the y values. All right. So this is the last graph, right? So if I will go to the table, see my x value, I'm gonna keep on going more negative. See, I can do this forever. Keep on getting more negative. What is y value doing? Keep on getting more negative. So that's what I mean by keep on going left and downward. Downward is where the x value is even more smaller, right? I can go the other way. Keep on going to the right. Okay, keep on going to the X value, keep on getting bigger, right? Go to the right side, it's bigger, and see what the Y values are doing, getting what, slightly larger at a time, right? And I can keep on doing that forever. So left to right, okay, we're talking about X values, down and up, we're talking about the Y values. And if you grab the square roots, let me go grab the square root one more time so you can see. If I go to the table, your domain, why does it start at 0? Well, because anything to the left side of the 0 doesn't exist. Because if you put -1 inside the square root, that's going to be imaginary number. That's why all the negative X values, Y values are error. So your domain starts at 0 and keep on going to the right. Okay. So just a quick description on these graphs. We'll talk more about them. All right, what does the interval notation is used to describe? So you can just go ahead and copy down what's on the lecture handout. At the beginning, you use to describe solution within a certain interval using inequality and domain and range of a function. Number 2, what is a correspondence between a domain and a range such that a range is a correspondence between a domain and a range such that every element in a domain corresponds to exactly one element in the range. Number 3, consider the following. All right, so make sure you go ahead and write down the answer on the side. Find the domain and write it as a set notation, enter your response. So use a graphic equation, okay? So start out with the open set, use with the brace. Go ahead and start your brace. And inside the brace, type in the X value. If it repeats, you just type in one of them, okay? So here you should only type in 1, 3, and 1, 4 for the domain. In the range, same thing. Start with a set notation or start with a brace and then just type in the Y value. So if you're repeating a Y value, you don't have to type in twice, just typing the number once. And then is a relation of function, not a function. So it would not be a function if you have a repeated X value. Okay. All right, so that will conclude our topic on functions and graphs.